आवाज आ रही है आपको? स्लो आवाज आ रही है। अब आ रही है? Still have some time. We can discuss what we have discussed last time, day before yesterday. Kindly accept my apologies for yesterday because I was traveling to Islamabad, and today also because I had to attend Anglo board meeting, and I just reached out. इसके लाना पड़ेगा, I can't hold it. So kindly recall that last time we start discussing NMR spectroscopy, fundamental concept of NMR spectroscopy. And the first thing which we have discussed was of distinction between NMR silent nuclei and NMR active nuclei. And then we discussed that NMR active nuclei, for example, argon or carbon 13 or fluorine 19 or N15, when placed under the influence of a magnetic field B naught, which is denoted as B naught, or more precisely called magnetic flux density, when you place the samples containing NMR active nuclei in a magnetic field, under the influence of a magnetic field, two things actually happen. One is that they orient themselves in allowed spin states. For example, for hydrogen, which we will commonly call proton, and carbon 13, they are spin half nuclei and they have two allowed states, plus half and minus half. So there would be two energy states, one in which nuclei are aligned to the magnetic field, direction of the magnetic field, and the other which is unparalleled, non-parallel to the magnetic field or opposite to the magnetic field, which is high energy state. So they orient themselves into these allowed spin states, allowed energy states, and they are not necessarily two. They can be 3, 4, 5, 6, 7, depending on the spin quantum number. Then we also discussed that this is not the only thing which actually happened. This is not the only thing which actually happened when you place your NMR active nuclei sample containing NMR active nuclei under the influence of magnetic field. The other thing which actually happened, which is even more important, is a precessional movement of these small tiny nuclei around the axis of the applied magnetic field. So if I start from that point, I can tell you that this is the applied magnetic field, B naught, and we place applied magnetic field always on the Z positive direction. So in conventional vector diagram, B naught is always placed towards the direction of Z plus. So these nuclei, they have two different types of spin. One is their axial spin and the other is angular spin. And this angular spin is because of a process called precession. They start precessing around the axis of the applied magnetic field. And this precession, the frequency of this precession is called precessional frequency. And this is a very important property in NMR spectroscopy. This is also called Larmor frequency. In respect of the person who first discovered this movement, Joseph Larmor, is also called Larmor frequency. And this precision frequency is directly proportional to the applied magnetic field. It is also dependent on the gyromagnetic ratio. This is what the advantage. And I think this was a point when we start discovering lots of interesting aspects of NMR spectroscopy. And as we proceed further, I would like you to take a breath and think what we have discussed so far, and if you have any ambiguity, any problem which you would like to discuss right now, we can do that, because now we would proceed further and we would go into a new paradigm explaining NMR spectroscopy with reference to vectors. Yes.
Highest concentration in blood gives that you have concentration.
Mic is not working. Hello. Any question? I can't hear you. Can you kindly repeat? Okay. Any question anywhere among the connected audience, remote locations, other universities? Here in the hall. It is very hard to believe that you don't have any questions. Karachi University. Dr. Riaz, Komal University.
Yes, sir.
Sargodha.
I have a question, sir.
Anywhere in 7 universities. Good to see you, Global University.
Thank you, sir.
Thank you so much. So, you want me to proceed further? You want me to move forward? Okay, inshallah. See, these were two diagrams. Mic up ठीक काम कर रहा है? क्या मतलब है? What is it called? Okay, these were the two diagrams which I showed you last time before finishing the discussion. And this is primarily just an understanding of representing the nucleus species under the influence of the magnetic field. So you see, this is your nuclei, because this is a nuclear motion, and it has its own axial spin, and under the influence of a magnetic field, never forget magnetic field. Magnetic field is ever present criteria, because you cannot have an NMR signal without the presence of a magnetic field. So magnetic field, applied magnetic field, is an ever present property. So when you have an applied magnetic field, you see this precisional movement. And we also discussed that this, along with the dependence of precisional frequency of nuclei on the magnetic field, the strength of a magnetic field and gyromagnetic ratio, which we have discussed quite extensively last time, we also discussed that this precisional frequency is a very characteristic property of different types of nuclei depending on their electronic environment. And this is precisely the reason that all the hydrogen in ethanol are not giving one single peak. As a matter of fact, they are giving 3 different peaks, because there are 3 different types of electronic environment. And since they have 3 different types of electronic environment, which primarily means that they have 3 different types of precisional frequencies, they would absorb radio frequency, which we have also discussed in the later half of the last discussion, at a different frequency. And remember, we also discussed that this is a property called in resonance, when the frequency of radio frequency is meshed with the frequency of precisional frequency, then you have absorption of photon, absorption of energy. And this absorption of energy is recorded in conventional NMR spectroscopy. And then I told you a long story that how NMR spectroscopy was developed as an absorption spectroscopy, how people used to sweep radio frequency and later magnetic field in order to get an NMR spectrum. And the philosophy was very, very simple, that as soon as the frequency of the incident radiations, which are your radio frequency, matched with the precision frequency of absorbing nuclei matched, then you see an absorption. And this absorption primarily means that you are absorbing an energy, and this energy takes nuclear species from lower energy state to higher energy state, and this is called excitation. This process is called excitation, and in the process there is an absorption of an energy, absorption of radio frequency, which people used to record. NMR spectroscopy was like a classical spectrophotometric technique in which absorption was recorded, in which absorption was then recorded as a spectrum, and people could see the difference in precision frequencies because of the electronic environment. People were able to see the integration, the number of protons present in a single peak, representing one peak, and in certain cases people were also able to see, along with the chemical shift, they were also able to see the couplings between two different types of. So this was the beginning of the NMR spectroscopy, and then I showed you a modern NMR spectrum, and I explained to you with reference to a very interesting question, that why magnet is so expensive. I tried to explain in a very non-technical way the architect of magnets, that magnets are really state-of-the-art results of the state-of-the-art engineering, metallurgy, electromagnet, superconducting, magnet physics, a number of other things which really make them very, very expensive. And I told you that the most notable difference between the old conventional NMR spectroscopy to the new spectroscopy in terms of hardware is superconducting magnet. And then I told you that the most important development, other than the development of hardware, was this concept of pulse Fourier transformation, which we would explain slowly. We will enjoy discussing this concept because this concept is very interesting. It has a lot to do with the signal to noise ratio. It has lots of manifestation on the development of NMR spectroscopy, so-called pulse Fourier transformation NMR spectroscopy. And I told you that the old absorption NMR spectroscopy, so-called CW, continuous wave, conventional wave NMR spectroscopy, is no more practiced anywhere, and now people are using PFT, which is a pulse Fourier transform NMR spectroscopy. And the technique is so common, and that the old technique has already foregone, it has already gone, that people don't even now say PFT, because it is assumed that all the NMR on the face of the earth now would have a pulse property, and they would have a property of converting into Fourier transformation by a mathematical tool. So NMR is pulse Fourier transform NMR spectroscopy. You don't need to say PFT because it is assumed. You would hardly find any NMR in the world except in museums, where you would have a continuous wave NMR spectroscopy, and who would use it now? So this was the diagram where I actually left, and I told you that that in order to simplify and in order to understand the concept of NMR spectroscopy, there are two ways of doing it. One is extremely complex quantum mechanical version of NMR spectroscopy, which requires lots of physical understanding of the physics, which requires lots of mathematical equation derivation, and a whole range of different complex phenomena. For the user's point of view, there is another approach which is called vector approach. And this is called vector approach because of a simple fact that nuclei are magnet, charge species. And magnetism is a vector property. And remember, vector has two properties, a magnitude and a direction. So it becomes very, very easy that you are actually dealing with all the magnets. You forget everything. That you remember now one thing, and that is magnetism. Your applied magnetic field is a magnet. Your nuclei are the magnets which are a vector quantity. Even the radio frequency which you apply, a new thing which I'm going to tell you, is a radio frequency, electromagnetic radiation, in which there is an electrical component and a magnetic component perpendicular to each other, absolutely in phase, carrying photon, which energy is directly proportional to the electromagnetic radiation's wavelength. Only the magnetic component is absorbed. So this is the magnetic component of electromagnetic radiation, which is actually used, which is the factor, and that's why the applied radio frequency is denoted by a term called B1. B1. So it is again a magnetism. Whatever is happening is in the paradigm of magnetism. So let's move forward and just show you a diagram which we have seen. I don't know why it's not working. Okay, it's working now. See, these are the two movements which I described last time. And I told you lots of, please do not really ignore the fact that all these facts, that these precision frequencies are directly proportional to the applied magnetic field, and there is a relationship between the precision frequencies and gyromagnetic ratios. They all are extremely important. Please do not forget the fact that the difference between the two energy levels of a spin half nuclei is directly proportional to the B naught also, right? And these facts have lots of meaning, which we would explain later. But let's first go into the word of vectors. This is your Cartesian coefficient. These are classical three-dimensional picture. You don't see any animation. Don't need to worry about these colored lines. Just this is your Z, and this is your XY plane. And now start using terminology is quite different from what you use in terms of normal three-dimensional coordinates. I would take this, I would use this direction as a longitudinal direction. I would use word called longitudinal, which is on Z, for me is a longitudinal part, right? And anything which is on XY plane is called transverse part. Remember these two terminology which I would use, that I would use the word called transfer from longitudinal to transverse. I would use the word longitudinal magnetization traveling transverse plane. So these terminologies are important and have lots of meaning. Now I want to introduce you to another very important concept as we move. So this is the classical picture representing the so-called vector diagram, and in this vector diagram, this is called block vector model. The whole concept of NMR spectroscopy, at least majority of the NMR spectroscopic methods, can be explained by using a block vector model. This block is not a block, is a block of a name of a person, Flex Bloch, who was one of the two founders of NMR spectroscopy. The other was Purcell. So this is called a block vector diagram, and I told you that you don't really need to have these globe, a nuclei in between. I would like to say that this is just an addition of insignificant nature. I would use use a single vector which is shown as a dotted line here, and this again shows this shows a precessional frequency, so-called a precessional movement around the direction of the B naught. Now, we all understand that there are literally trillions and zillions of nuclei, not one or two nuclei. And we all understand that when you provide them an applied magnetic field, you have orientation either towards the magnetic field, unparalleled, or opposite to the magnetic field. Now, what is the population difference between these two? This is an extreme concept. You see, if they are exactly the same, it doesn't really make much of a sense. There was an old concept long before the advent of NMR spectroscopy, and that concept was called Boltzmann axis. Boltzmann is a name of who first discovered that the world is stable because there is certain number of species in lower energy state which are in axis. The stability factor in lower energy state, there is always a tiny axis or a big axis or whatever. This state, the difference in population is in NMR spectroscopy. This difference is unfortunately very, very less, and that's why NMR is inherently very insensitive as compared to any other technique. You see, when you have UV spectroscopy or IR spectrophotometry or UV spectroscopy, all the electrons of a non-bonding orbital would travel to valence electron from one orbital to the other orbital. Everything would excite, would need to be excited, right? In terms of IR spectroscopy, you would have molecules which are present in your sample would have a molecular motion, all of them. But in this case, the population you are really interested in, the population difference is extremely tiny. And I can give you a number, but it's insignificant. At about 400 megahertz NMR instrument, and if you have a million population, the difference is about 13, 40. So this axis population is called Boltzmann distribution axis. But I want you to just stop that point and try to appreciate something different. All of them are vector quantities, right? Some are orienting towards the opposite to the magnetic field. Of them aligned to the magnetic field. This is your lower energy state, and this higher energy state. Please do not confuse to the conventional. Always have a lower state low, a higher energy state higher. This is a convention that NMR is sometimes upside down, and sometimes you understand upside down, of course, right? Okay. Now, all of them are vectors. It is a cone, it's a cone which represents the precession frequency. So you have a cone of these precession frequencies. You see, all of these vectors have the same magnitude but opposite direction. You agree? And therefore, they all should cancel except axis, right? Except this tiny little axis. This tiny little axis, Boltzmann distribution axis, is in few numbers if you have a million population. Of course, you don't have million nuclei, you have zillions nuclei, and this population can be several hundred or thousand or whatever. But always remember, this population is really very little, very little. Now, if that I have cancelled all the vectors except a few vectors which remain and representing the Boltzmann distribution axis, and I want to combine them together, you should not really have any problem because vectors with the same magnitude and same direction can be combined together into magnetization vector. So this is the M naught is representing the axis population in lower state, and it is called bulk magnetization vector or Boltzmann distribution axis. Boltzmann is representing the Boltzmann distribution axis. And if I tell you one fact, that this Boltzmann distribution directly proportional again, magnetic field and gyromagnetic ratio, you should not be surprised because everything is with reference. And remember, this Boltzmann distribution, net magnetization, the axis magnetization is your NMR signal because that is what absorbed, right? So this is an M naught. Always remember, this is an M naught, B naught. B naught is a applied magnetic field. Okay? Naught is on the direction of the applied magnetic field in lower energy state, representing the excess of population in lower energy state, which is called Boltzmann distribution axis. And this net magnetization vector I will call longitudinal magnetization, because now I've decided that I would not use the word Z. It is a longitudinal magnetization vector. Okay, this magnetization vector is the vector which represent Boltzmann distribution axis. Now, have the same treatment, exactly the same thing. This is your M naught on the direction of applied magnetic field, longitudinal magnetization. Longitudinal magnetization. I want you to recall what I said last time, that precision frequencies are the actual property of molecules, of nuclei. And if you can measure by any procedure the precision frequencies, for instance in ethanol, the 3 different precision frequencies of 3 different types of proton can be measured by doing anything else, then you don't need to do anything else. But you can't do it, and therefore you need to bring another force which is called radio frequency. And now, I don't know whether this would work. Anyway, okay, forget it. Crucially important concept. This is your B naught, direction of B naught. This is your M naught representing the Boltzmann distribution axis. And now you want to bring another force which is called radio frequency, incident radiations, electromagnetic radiation, magnetic component of radio frequency, which is called B1. And this B1 is given from the transverse plane, from anywhere in the transverse plane, anywhere in the transverse plane, perpendicular to the magnetic field, to the magnetic field. Remember what happened in the first instance. As you applied the magnetic field, there was a property of called torque, because everything either aligned or opposite has really turned into a specific direction, which is called torque in physics, right? So remember, the first torque which has created was the torque because of applied magnetic field, right? Now you are bringing another force in the system, right? Another force in the system, and this force is your radio frequency called B1. I want to tell you, if I ask you, if you turn on radio frequency oscillator is a machine which produces radio frequency. And I will tell you that radio frequency oscillator is a very flexible machine because it has 3 different parameters. So-called frequency power, how much radio frequency it gives. It has a property of frequency width, how wide the frequency is. And the third is duration of the radio frequency. It has a number of different. There's something wrong today because I've seen at least 5 people constantly yawning, snoring and all. So it never happened, It never exceed, even in 200 people, it never exceed more than 2. And today, in less than 40 people, we have 5 people. There's something wrong, I don't know what I'm doing. Really sorry. Feel that I'm sleeping? Okay. Anyway, don't worry about that. So this is all right. I mean, मैं चाहता हूँ आपकी ज़िंदगी में सुकून हो, तो बहुत important. किसी तरह भी हो, चाहे NMR पढ़ के हो या who cares, you know, जिंदगी में सुकून सबसे important है. Anyway, apart from this sukoon which you can get from NMR, you can get lots of important information from NMR spectroscopy. You see, I want to invite you to think. You are an observer in this three-dimensional coordinate system sitting outside. You have two forces now acting on your nucleus species. Before the application of B1, your radio frequency, you have a longitudinal magnetization created because of a property called torque, right? Towards the direction of the B naught. Now you see another force in action. And this force in action is again a magnetic field of radio frequency. Now when you see this, you bring another force. This tiny little nuclei would do something extremely strange. And that strange thing is that they would, instead of moving around the B naught, they would start moving around the B1. Now you have a second force in place. This second force in place, exactly the same thing happened, and this is called torque again. And the difference is that this is the direction of the magnetic radio frequency, and they would start moving. If this is x, then you would have a movement of this longitudinal magnetization vector to y to minus z to minus phi, and then plus z, and constantly. So when you bring a perpendicular force, the second force towards the direction of longitudinal magnetization vector, it start moving around it, right? It's called second torque. In order to distinguish between the angular and precision frequencies, this particular movement is called nutation. The word called nutation, N-U-T-A-T-I-O-N, nutation. Second force which is applied, because now things are getting little extensive, little difficult. You have radio frequency provided to the system, and this, because of this radio frequency, your magnetic your nuclei, so-called M naught, is now start moving in the direction of the applied field, right? Moving in the direction of the applied field. And they would continue to do it if you have a constant radio frequency applied, right? All the time. If you have a radio frequency applied all the time, then you would have a constant movement of this. If I tell you that this Richard Ernst, a fellow, very first time, has actually introduced a term called pulse, radio frequency pulse, which in an easy language is a burst of radio frequency, turning on radio frequency and turning it off. And there is a duration of the time in which you turn off and turn on and turn off. If you apply this radio frequency as pulse of a specific duration, I invite you to think what would happen. For instance, if it takes 7 microseconds to bring this, or let's say if it takes 10 microseconds to bring a radio frequency pulse of 10 microseconds to bring this magnetization back to longitudinal magnetization vector, how much time it would take to bring it to the minus z? Half circle. Full circle take 10 microsecond. Half circle, 5 seconds. And if I tell you 2.5 seconds, where it will be? Where it will go? Why? But why? Why not minus x? Why not anywhere? I totally agree with you that this magnetization vector will come on the transverse plane. Transverse plane pe aa jayega, this will come on the transverse plane. One thing which you have understood so quickly, promptly and efficiently is the concept of pulse duration, right? One thing which you need to understand upon it is the fact that you have a power which deals only with a particular type of a nuclei. So the radio frequency, your radio frequency oscillator has a capacity to generate radio frequencies of different types. Radio frequency, always remember, has a width, right? So it can generate radio frequency which is specific for carbon, which is specific for fluorine, which is specific for N15, which is specific to Hertz. This particular radio frequency is specific to, let's assume, hydrogen or a proton, right? So the power of radio frequency is set for proton, right? Okay. And the duration bring this magnetization vector to anywhere on the plane. And I want to challenge you that you tell me another NMR spectroscopy, another spectrophotometric technique in which you can predict where the electron would be or where the molecular motion would be. You would never be able to predict it. This is the only technique in the world where you have the capacity of knowing where it would be. You told me right now that it would take 2.5 microsecond to bring it to the XY plane, transverse plane, right? The predictability of this technique is mind-boggling. You know, NMR is different from everything else because you have a great tendency and capacity of understanding where it would be as the result of a predefined action. Right? No other technique would tell you. Now, if I tell you that I want to bring it to Y, exactly positive Y, you would ask me that that you give a pulse of 2.5 microsecond. I said, I don't want to talk about duration. I would like to talk about the end result. I would say a 90 pulse rather than 2.5 microsecond because it can be different in different spectrophotometers, right? Let's talk about the end result of an operation. And this pulse is in operation, and as a result of this radio frequency pulse, I have a tip of, I have a torque of, I have a nutation of this longitudinal magnetization vector to 90. And this is an angle called theta, 90 theta tip angle. You can just name it, there are lots of names in it. 90. So for me, it is a 90 pulse rather than a 2.5 microsecond. Because you can have a different duration, different in different equipment. The only thing which I want to make sure that you have the capacity of bringing this magnetization vector from a longitudinal axis to the transverse axis. This is called 90 pulse. Now I want to tell you that you can do it in a much more predictable manner. For instance, if I tell you that there is a rule of thumb, right hand rule of thumb. So if this is the direction of the radio frequency pulse, the movement of this longitudinal magnetization vector would be if 90 is. So where it will go, if I provide a radio frequency pulse from X direction and I called it a 90X, 90 is the end result, X is the direction of the radio frequency, where it will go, plus phi. And if I tell you that I want to bring this magnetization vector to minus phi, where I should place my radio frequency oscillator? Minus X. And which angle I should give? The tip angle kitna hona chahiye? So what it would be? 90 minus X. Isn't it? Huh? So no, 90 minus X, right? Minus X is the direction of the pulse. If I want to tell you that I want to bring it to minus, I want to bring it to plus X. I want to bring this longitudinal magnetization vector on a transverse plane, but on plus X, where I should have my my radio frequency oscillator किधर से जाएगा? How many people will agree with this? 90Y. One response is that I need to have a 90Y pulse, but it will bring it to minus X, right? And you want to bring it to the X, then minus Y. Now, you should really have the same feeling as I have. Extreme excitement. वो जिसे कहते हैं ना कि really? नहीं? Which technique in the world will have the capacity of, will give you the capacity of moving these tiny little magnets to the place where you want and play with them? It's only NMR spectroscopy. This is the reason why NMR spectroscopy has become an absolute icon of a control on the process of the spectrophotometric response on nuclear species. I want to further elaborate. Let's say I want to bring this longitudinal magnetization vector to minus Z, where I should have my radio frequency oscillator placed. $180 तो ठीक है, it makes sense. And remember, 180 is the result of a certain duration of a pulse. Never forget the fact that this 180 is because of a certain duration of a pulse. Never forget it, because in the NMR you need to set it, right? And always remember the fact that you must also set the frequency on the nuclei you want to play with. If you want to play with hydrogen, you need to have a radio frequency oscillator for hydrogen. If you want to play with carbon-13, then you set your radio frequency oscillator for carbon-13, NF19, NN15. So you can just play with it. If I want to bring proton magnetization vector to 180 minus Z, from where I should have my wonderful anywhere, right? It should not really make any difference to it. It can be anywhere. It is 180 pulse from anywhere. But if you want to bring it to the XY plane, then you must really have a predefined position of your radio frequency oscillator. If I want to tell you that I don't want to do that, I don't want to bring my magnetization vector on negative Z direction, because it doesn't really help me. And I want to tell you that because of the fact that you can only place detector on XY plane, transfer plane, then you would agree with me that if I really want to do something useful, or if I really want to detect this magnetization vector, I must bring this to XY plane, right? Tell me why I cannot place my detector on the direction of Z, either positive Z or a negative Z, because of a simple fact that you have ever-present magnetic field. And if you point out the detector towards ever-present magnetic field, you would have nothing but only the magnetic field effect, right? So if you really want to play safe, you want to bring it to XY plane, and you want to have a detector on XY plane. If I want to tell you that radio frequency oscillator is on X, and I want to bring it, and I want to have a detector on this point, would you agree with me? If I want to keep the radio frequency oscillator on X, and I want to have a detector on minus X. You see, the most interesting thing is that people who were sleeping 5 minutes ago, they're now smiling. This is the most exciting thing. So, would you agree with me? Can I place it? Why I can't? But this is not true. As soon as I bring this magnetization vector on xy plane, I turn off the radio frequency oscillator. This B0, this B1 is not ever present property. It is a pulse of radiation which you use to bring your magnetization vector on xy plane. Okay? Now, I want to ask you another question. As soon as I bring this M0 on xy plane and turn off the radio frequency pulse, what will happen? The second force came into the picture, gone. What will happen? Again, very nutrition has gone. This would again start processing around ever-present magnetic field, right? So this magnetic vector, this M0 from longitudinal to transfer plane, when I bring it here and assume that you have only one proton, let's have a water molecule, you bring this, when I say one proton doesn't mean that one hydrogen, both hydrogens are same, therefore I said one proton, one type of proton. When I bring it to the xy plane by using a B1 radio frequency oscillator, turn it off, it is on the Y, what will happen? Will it remain B on Y forever? It relaxes back. It has to relax back because this is an excitation state and it needs to achieve a thermal equilibrium. And in order to achieve a thermal equilibrium, it needs to relax. But one thing also, see, will it really relax in a manner like this, that I bring it to the Y plane and then it goes back to the Z plane? Can't, because you have ever-present V0. So it was actually processed in the axis of a V0 on XY plane. If there is any confusion at this stage, please ask me. Yes. We do lots of time. We do for variety of different purposes, but in order to detect, we always bring it to XY plane. We do it for variety of different types of purposes. I want to tell you one thing. You have a proton carbon. You want to detect carbon without a proton, without the coupling with the proton. What you would do? You would make sure that your proton is not on the XY plane. Right? So in order to differentiate between different types of proton and create a multiple quantum, I don't want to use this word. If you want to create a quantum incoherence, God forbid, it is a term which is a nightmare. But I will tell you one thing, it is a quantum coherence. All of the protons, 30, 40, 200, 2000, 5000, 20,000, 100 zillion thousand, all of them, when you would provide them radio frequency, they would all come at the same time. Yes, please.
Hello, ICCBS. I have a question. If we remove the radio frequency B1, then the plane again goes to the longitudinal axis, Z axis.
ICCBS think that it would go back to the longitudinal. But it would go in a very interesting way because it would persist around the ever-present V0 and slowly lose the angle, like an umbrella. So it would move like this and slowly move up to the level of when it goes to the thermal equilibrium. So the answer of your question is yes, it will go to the longitudinal axis because that is the thermal equilibrium state. but it would go by relaxation, and this relaxation is a process in which it would retain the precision frequency around the ever-present B naught and slowly lose the tip angle backward to eventually go to the longitudinal axis. So that is like an umbrella, which umbrella closes. You close the umbrella, it really closes like this. Okay?
Thank you.
Any other question?
Thank you, sir.
You're very welcome. Not working. This was an attempt, failed attempt to show you that this magnetization vector move around. This is your m naught, which is on xy plane now, moves in the direction of the applied magnetic field and slowly lose the angle and goes back to z, right? So if you're showing the longitudinal magnetization vector, it grows from 0 to full line. You know, if you want to say that the resulting this is the process of relaxation. I hope you can appreciate this. Yeah, very simple. That magnetization vector, which is on xy plane, once you turn off the radio frequency, you have only one force present, and that is your B naught, and it has to move around B naught. It is a larger magnet. It has to move around with the same precision frequency which is inherent to this particular nuclei. But at the same time, it would have to go back to the thermal equilibrium position, and therefore it will lose angle. So it would move like this, and slowly it move up. Okay? Clear or not? किसी ने कहा यूं, किसी ने कहा यूं, किसी ने कहा यूं. वो मुझे लगता है पल्स एंगल हो गया है. अभी उस स्टेज पे आया नहीं है यार. I want you to wait for me. And I will tell you something. You see, I'm using this word called turning off the radio frequency. रेडियो फ्रिक्वेंसी इसको लाने के बाद टर्न ऑफ नहीं की जाती, बल्कि रेडियो फ्रिक्वेंसी इज टर्न्ड ऑफ when it is there, you know. So it is the end result. There is a fine difference between them. Radio frequency is bringing it to XY plane, right? So you are using a radio frequency duration in order to bring it anywhere in the XY plane. Now you agree with me the fact that you can bring it anywhere on this three-dimensional coordinate system. Anywhere, right? You can bring it to minus 180, you can bring it to minus 270, 270, or you can bring it to 380, and you can bring it anywhere on the 360, sorry. And you can bring it to anywhere on XY plane. By using a simple understanding that the duration of the pulse can be set to bring this magnetization vector anywhere. And I also told you that the direction of radio frequency oscillator, direction of the radio frequency incident radiation, so-called radio frequency oscillator, is very important, because by using a right-hand thumb rule, you bring it to anywhere on XY plane. Okay? Yes, no? Any question from the 7 universities connected? Okay, so if you allow me, I would like to move forward. Okay, exactly the same thing is called spin dynamics, gymnastic of spin. This is your longitudinal magnetization vector representing the Boltzmann distribution axis, the axis in the lower energy state. This is your radio frequency pulse. Now, if I tell you that I don't need to make this funny looking machine and this more funny looking arrow, and if I just tell you that I want to use the word, I want to use a diagram like this: radio frequency off, and radio frequency on, and then radio frequency off, on, off. So when you turn on the radio frequency and turn off the radio frequency, it is your pulse and duration of pulse, and this would bring your would bring your magnetization vector anywhere where you want. You have the capacity of bringing this magnetization vector m0 anywhere. This is the tremendous capacity which you have it in NMR spectroscopy and none other technique. No other technique, right? Anywhere on XY plane, anywhere in between. I mean, it's not necessary that you have a 90 pulse. You can have 40 pulse also. You can have 30 pulse. You can have 60 pulse. You can have 140 pulse. You can have 220 pulse. You can have any pulse. But one thing is sure, that you would know where it is, which you don't know in any other case. In any other spectrometric technique, you would never know what actually happened. You just record the end result. You record the thermodynamic end result, which you do not record is a kinetic process, so-called dynamic process, and this is the dynamic process because you are capable of recording. You brought it to the transverse magnetization vector. Totally agree with you. It depends on the width of the precision frequencies. You see, if you have several protons of a variety of different types of precision frequency, you need to have a broad radio frequency. Broad radio frequency because you want, you see, your question would now be answered that you want everything to be absorbed at the same time. So you need to have a broader one and you need to have a stronger one because you're changing the torque and you're changing the torque into nutation, second torque, right? So this is the spin dynamic. Now, again you see radio frequency oscillator, bring it to this plane, and then radio frequency detector, this is the detector which detect. Now, I want to ask you a question. You see, all of them have actually absorbed at the same time because you gave a strong radio frequency pulse broad enough to excite everything in the in the sample, right? All of them, right? It's different from the absorption spectroscopy. Remember, in absorption spectroscopy, you were sweeping, right? Here, you excite all of them, and now you have a situation which is called coherence. It's called quantum coherence. Quantum coherence. Everything is coherent. All of the protons, if you're dealing with the proton, all of the proton have absorbed at the same time and came on the transfer plane at the same time. My question is, would they all go back to the longitudinal position, thermodynamic position at the same time? Why not? So it means that this coherent signal had to be split into many types because they all have different precision frequencies. Assume that this is only a water molecule, only one type of proton. Assume it for the simplicity in order to understand. You have a detector in front of you. Now, this magnetization vector on transfer plane is moving on XY plane, right? XY plane. So it is recorded by the detector. and it slowly go up, right? It slowly go up. So the detector would record it, and it would record the decay in the magnitude of the signal, right? And this process of relaxation is very, 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 very important, because the reason that absorption you are not recording, it is not an absorption spectroscopy. It is, I don't know what it is. Honestly, I don't know. Nobody has ever given it appropriate name. It is not an emission spectroscopy, because emission spectroscopy is primarily means that you give the wavelength and you get the wavelength, right? You give radio, you give IR and you get an IR in return when it relaxes, right? UV, it back UV. Problem in NMR spectroscopy is that it never gives radio frequency signal. Your detector never receive a radio frequency signal out of this. So it is not an emission spectroscopy at all, right? Now this energy which is pumped into the system by a phenomena called pulse, by a process called pulse, radio frequency oscillator, through a radio frequency oscillator, need to be released out of the system in order to achieve the thermal equilibrium. This is fundamental fact of life, that energy need to be released in order to go to the equilibrium state. Now, this energy in this case is radio frequency, right? Problem is that radio frequencies are not detected. Radio frequencies in cases like this, radio frequency, this excitation of the nuclear species, and I want to confuse you to the utter level. This radio frequency, which is actually absorbed, convert into variety of different types of energies. One is a very tiny little thermal energy, so tiny that you cannot even measure it. If you can measure it, then I would not use the detector, I would use a thermostat, to be honest, right? The other is oscillations, which it will give it to the neighboring species. And I will tell you what neighboring species are. And the third is a very small electrical component. And this small electrical component is the one which is detected. So you have very interesting, you have this nuclear species moving on XY plane and passing in front of a detector. Every time it passes in front of a detector, it creates a very minute femtoampere impedance in AC current, alternating current, which is detected by the detector, not the radio frequency. Radio frequencies are not detected. So I don't know what you will say. It is not an emission spectroscopy. It is not an absorption spectroscopy. It is not a thermal relaxation. It is not any type of oscillation relaxation. It is, I don't know what. That is the reason why NMR, nobody wants to touch the whole process of NMR, of the whole process. It is detected a very small count. Other thing is that in all spectrophotometric technique, if you give 100 UV, you would get 100 UV in relaxation process, a near complete recovery of energy in order to achieve thermal equilibrium. In this, only a minute fraction of the energy pumped into the system is detected. Now, you see, this technique becomes extremely insensitive by virtue of many things. Number one, this Boltzmann distribution axis is so little with which you are playing with. Number two, not all the energy is actually recorded, and it just relaxes in a multiple way. And I want to tell you that relaxation is important. You see, in order to give energy, you must really have two different things. You must have a radio, you must have a receiver, you must have a species which absorb energy, and you must have a medium through which the energy is absorbed. Radio frequency has a multiple problem. It has so many of them and none of them at the same time. For instance, it need to relax. It need to give energy, right? Detector is only detecting a very small component of electrical impedance as the alternating current. Where else this energy would go? This energy would go by creating a situation called in resonance. Remember, energy cannot be absorbed or cannot be released without a condition called in resonance. Unless you have an in resonance, you cannot transfer energy from one species to the other species, either from the incident radiation to the receiving oscillation, or from receiving oscillation to the other receiving end. A multiple problem. Agree? Okay? Chale, let's. Now, there are several types of relaxation. The only two are taught in NMR spectroscopy. There are a number of other things also. You see, even now people are trying to develop so-called thermostats which can detect the thermal energy coming out of these species, because there is a slight temperature which is so tiny that it can't be detected with the regular thermostats. But there are two different types of relaxation. One is called spin lattice relaxation. Never forget the word spin. When I say nuclear, when I say longitudinal magnetization vector, when I use the word m naught, always remember that they are spins, and this is a technique in which the energy go from your nuclear spin to the lattice, and lattice is your environment, space around it. Everything else around it will become the sink of absorbing energy as soon as they become in resonance with the hydrogen or with the spin. So, spin lattice relaxation. Energy is going into the environment. Energy is going into the environment, which is the major way of relaxation, but not the only way of relaxation. Please understand, because when we will discuss nuclear over-Auger effect, you would know many other surprising things. So this spin lattice relaxation is the major or the most important way of releasing energy, and this is an energy which actually going out of a spin system into the atmosphere lattice. And what this NMR tube में क्या atmosphere होगा? What is the environment in NMR? Solvents and impurities and paramagnetic oxygens, a whole range of different metallic species, the impurities of all types. Various types of impurities. You can't even detect them because remember, detection limit is the limit to detect. Right? Things are present, can't see them because you have not really reached to a stage where you can detect them, right? Always remember. Detection limit is your limit to see. So there are plenty of different species, even in the purest solvent, where this energy goes, right? Where this energy goes. So this is the main mechanism through which relaxation takes place. The other is the process called spin relaxation. Spin relaxation. You see, most appropriate system to transfer the energy is from one nuclei to the other nuclei. because they are almost very close to the same oscillation. So if I have three different nuclei in ethanol, three different types of proton, then one proton will give energy to the other to the first one. They all change energies. But is it really a relaxation? It's not a relaxation, because it is just the total energy content. Total energy content of the system is not changing. So it's not truly a relaxation in a homonuclear system. I want to confuse you again. It's not truly a relaxation process in a homonuclear system like proton-proton. But it can be an efficient relaxation process in a heteronuclear system. From carbon to proton, yes, the content of energy in carbon species are decreased by spin lattice relaxation, right? So, therefore, it is called a relaxation mechanism. We have a different types of proton. Who cares? But the overall molecule would have the same energy. You know, it just this. I give you 1,000 rupees, and you have already 100 rupees. So, two of us own 1,100 rupees, right? Whether you have 1,000 rupees, no, it really matters. No, sorry. But collectively, HINA and ICCPS together would have 1,100 rupees. Okay. So the overall relaxation in homonuclear system, spin-spin relaxation, is not a very serious thing, to be very honest, but it has other manifestations. Other manifestations are important because it is the main mechanism through which coherence is lost. You see, जो बंधा हुआ है ना, the big signal which you get at the end of a burst is spread because of spin-spin relaxation. Right? Forget everything. Don't be confused. Just remember there are two different types of relaxation. One is called spin lattice relaxation, which is T1, a big T1. And the other is big T2, right? T1 is the most important relaxation mechanism through which most of the nuclear species lose their energy and goes back to the thermal equilibrium. Now, relaxation is a process of losing energy. But this losing energy is manifested with the fact that it is moving away from the XY plane, isn't it? If it doesn't really lose energy, it would always be on XY plane. Agree with me? Right? It means that in order to see that how soon, how quickly, how promptly this nuclear species is losing energy is only possible by using a detecting system, right? You need to have a detector, and you need to, now you're detecting what? Not a frequency, electrical impedance, and the time it takes to go away from the detector site. Detector की आंखों से दूर होने में जितना वक्त लगता है, the time it takes from the XY plane moving out of the site of a detector is the time which is required to convert a transfer magnetization vector to the longitudinal magnetization vector. You know, it slowly loses. And this particular quantity is a time. Is a time. Right? Time. So at the end of the day, what you are getting is not very nice looking NMR spectrum, but you are actually getting the time. That is the problem. Now, I would really like you, it is available on the website. I would like you to answer this to yourself. Explain the behavior of spinning nuclei in the absence of a magnetic field, under the influence of a magnetic field, and when RF is applied. Three different conditions, right? In the absence of a magnetic field, in the presence of a magnetic field, and when along with the magnetic field you also give radio frequency. You must understand this whole concept because this is what the basic component of NMR spectroscopy is. Second question which I would like you to answer, what will happen if the radio frequency pulse is applied constantly? So you're answering to yourself, not to me. I don't care whether you answer. Okay. And this, from the discussion so far, can you summarize the factors, very important question, affecting the population difference between the lower energy state, let's say N alpha, and the upper energy state N beta? And how is the population difference related to the NMR signal? This is something which I would like to answer right now, because I deliberately wanted to wait until the time we all understand. You see, when we applied magnetic field, the two energy levels are created, right? The difference in this energy level called del E is directly proportional to the V naught applied. And I told you that the population difference is your NMR signal, right? And I also told you the fact that del E is directly proportional to the V naught. So if you have a 100 megahertz NMR, let's say a 1.5 Tesla NMR machine, you would have a difference in energy so much. The population difference would be only tiny. Why? And when you have, let's say, 8.8 Tesla machine, 600 megahertz, 700 megahertz, the population difference increases, and the del E increases also. So when del E increases, the population difference increases also. Why? What? Absolutely. When the energy gap is less, there is a possibility of interstate transfer. When you increase the energy difference, the population remain on their respective sites. That's why you increase the population difference. And population difference is your NMR signal. And this is the reason why people have been doing a lot of work to develop very high field NMR, very high field magnet. High field magnet, more del E, more population difference, more signal. Understood? Yes. Yeah. If you have more than two states, the interconversion between these two states would exactly have the same behavior. When you increase the field strength, the difference between these energy levels would increase, and the population difference, whatsoever it is, between 3 or 5 or 6 states, would be increased because the difference in energy level is increased. Okay. Then three energy levels would have an increased difference in their energy levels, and the population between three different levels would increase subsequently, because the interstate possibility of interstate, I don't want to confuse you, but there is a phenomenon called induced emission. I mean, I hate this phenomenon. I really spent a lot of time on it, and I eventually discovered that if I tell this thing, I destroy myself forever. Please forget it. It's called induced emission. You know, there is a phenomenon called induced emission. What's that? Okay. The difference in energy of del E of different states, either 2, 3, 6 or more, increase as you increase the V naught, field strength. And therefore the population difference between these energy states would also increase. Now, one thing more. When you have a 3-state, the transition is not only one. The excitation would have three different values. They would excite in three quantized state. That is the reason why you would have three different signals. At least for three, there would be two different absorptions. One for the center one, and remember, if we have 8, 9, or 20 different states, quantized state, the lowest one is the one in which you would have absolutely perfectly aligned. The highest is the most non-parallel, and in between is in between. Spin number 2i plus 1. You know, if you have I2, then you would have 5 different. So there are different. Always remember that these quantized states are the state in which you would all have population. And
Excuse me, sir.
Just let me finish. This Boltzmann distribution axis is equally valid in all type of it, that lower energy states would have slightly higher population than the higher energy states. Yes, please. Go ahead.
Actually, the spin lattice relaxation and spin relaxation is a little bit confusing. Can you explain a little bit more?
Spin lattice relaxation. Yes, I can explain to you. No problem. If you go back, spin lattice relaxation. You see, when you pump in the energy into the spin system, into your proton or carbon-13 or whatever, specific frequency, specific duration, this energy need to be released out of the system. This energy need to be released out of system, and in this particular radio frequency case, this energy is always released as a non-radiative energy. Always remember, is a non-radiative energy. Radiation never come out of the system, because radio frequency is so weak that it cannot really release as a radio frequency. It is non-radiative. Now this energy is going to be transferred to a variety of different types of species around it, right? For example, solvent molecules, for example, metal impurities, for example, paramagnetic oxygen, which is a very good sink. You know, it can absorb lots of energy in order to become. These species which are actually present around the molecule, minus molecular entities itself, component of different molecular entities are not included. Other than the molecular entities, anything where this energy can be transferred is called spin lattice relaxation, T1, and this is the main reason, this is the main way of losing energy and achieving thermal equilibrium. Okay?
Okay, thank you.
The spin lattice relaxation is when you transfer the energy from one spin of the same molecule to the other spin of the same molecule. So overall energy level do not really relax back. It really function in a very different way. And so this was a question which I wanted you to answer, that from whatever we have discussed, what are the factors affecting the population difference between the lower energy state and the energy state? What? Magnetic field strength, then paramagnetic ratio, and this is the field strength. Any other question?
Sir, I have a question.
Sure, speak loudly.
Parman Ali from Bombay. Sir, first explain the in resonance, like you have earlier said. And the other one is, sir, please kindly explain the in resonance.
In resonance. Okay.
Yes, sir.
Sure.
And secondly, is the absorbed energy and relaxation energy of the system same? Are there any difference in them?
Okay. Let let me first explain in resonance. You see, in order to transfer energy from one to the other, it has to have a same wavelength, and it is called constructive interference between two species. Constructive interference. Constructive interference is the interference in which you have exactly the same wavelength, right? When you have the same wavelength, then you are capable of transferring energy from one species to the other species. For instance, incident radiations to the molecular species where you have. And this particular phenomena is called in resonance. In resonance. Without in resonance, and in resonance takes place in everything. In UV, in IR, in X-ray, in everything in which energy is transformed from incident radiation to the molecular species. This in resonance is a requirement. Remember, matching of the radio frequency doesn't really mean that they have the same energy. Please always remember, because incident radiations carrying photons with it, right, which are actually transferred. Energy is transferred when you have a constructive interference of the wavelength. Energy is transferred, right? Energy, and this process is called in resonance. आपका दूसरा क्वेश्चन भूल गया हूँ, क्या था?
Is the dark, yes sir, I'm repeating sir. Is the dark energy and relaxation energy of the system remains
Yeah,
same
that
as
is, yes,
yes.
you could first that if it absorbs the radio frequency, it should give radio frequency. The actual question is that if it absorbs energy, it must give energy back. You know, the real issue is that energy absorbed, energy emitted. Without releasing energy, it can't go into thermal equilibrium. In all different types of spectroscopic technique other than the radio frequency, this energy release is radiative in nature. UV absorption, UV emission, IR absorption, IR emission, microwave absorption, microwave emission, X-ray absorption, X-ray emission. But in radio frequency, this radio frequency is so weak that it is not released as a radiative force, but it released in a multiple component. And this multiple component can be thermal, electrical, or oscillating, a different type. Electrical is the one which you can read through your detector. But the other goes into the environment, which there are so many other species which receive it. There is a slight increase in temperature, tiny increase in temperature, which is difficult to be measured, but it is believed that a part of this radio frequency is also released as a thermal energy. Remember, जो microwave में आप देखते हैं, what is the microwave? Philosophy of dipolar molecule interacting with the microwave, it converts into heat. So one form of energy can be converted into other form of energy also, depending on the nature of energy. Okay? The fourth question is, there is only a slight excess of nuclei, so-called Boltzmann distribution excess in the ground state and in the high energy state. Would you expect in the case of C13 experiment for the same population difference to prevail as compared to proton? No, it's important. It is important because we know why C13 is insensitive. And this is the reason why there's so much of development took place in NMR spectroscopy, both in hardware and in approach. And I want to explain before I finish a very important approach which is based on this phenomenal change in the way NMR is conducting from absorption to a pulse NMR spectroscopy. really sweeping the radio frequency, detect mostly the baseline, taking zillions of years to record a few spectrum. You go into a dimension when you excite them all together and you record the process of relaxation, right? It's a phenomenal change. Nothing like this has happened in any other spectrophotometric technique. Nothing like this. UV spectrometry and IR spectrophotometry and X-ray and neutron diffraction is all same as it was earlier. There is advancement in instrumentation in terms of detection, in terms of more of or of electronics and display system, but the fundamental change in the process of recording in spectrum has not taken place except in NMR. Here you have fundamental departure from an original absorption spectroscopy, very which is not even an emission spectroscopy, right? So question 5, explain what is meant by the Lama frequency. I want you to understand Lama frequency to the maximum limit, because Lama frequency is the frequency which define an electronic environment of a nuclei, or correctly, electronic environment defines the Lama frequency. Okay. And I would also like you to understand the magnetogyric ratio or gyromagnetic ratio. The correct word is gyromagnetic ratio. And how does it affect the energy difference between the 2 states or 3 states or 5 states or 6 states, and nuclear species sensitivity to the NMR experiment. Now, sensitivity is primarily means population difference, right? Population difference, because that is what your NMR signal is. Your NMR signal is the population difference, because that is the only signal which is capable of going to the XY plane, right? Okay, so I want you to understand this, but I want to leave you to this particular situation. You see, remember when you give a 90x pulse, and I should start talking like an NMR spectroscopist. Yes, question? NMR spectroscopy, I want to give you a sample in which I want you to detect protons. And I want to give you an instrument. And I want you to record for me a proton NMR spectrum. Any question?
My question is that why
I cannot hear you. If you come close to the mic, I might be able to hear you.
I am Jal Paras from Bhuman University.
Yes?
My question is that why and in which condition we use the different RF pulses, for example 30 degree, 90 degree, 60 degree pulses. Why and in which conditions we can use the different RF pulses?
I will really appreciate if you come very close to the mic, because it's very hard for us to hear you.
My question is that why and in which conditions we can use the different RF pulses, for example 30 degree, 60 degree and 90 degree pulses.
In which condition we use RF pulses?
Different RF pulses.
Different RF pulses. Yeah, this is a little premature, because I want to explain you right now that if you want to record a proton NMR spectrum, a simple proton NMR spectrum, the first fundamental NMR spectrum, proton NMR spectrum, then what you would do? That is what I would like to tell you, and here you would understand why different pulses are given. I give you an example, and I want you to record for me a proton NMR spectrum. What you would do? Always remember that you have a detector on XY plane, and I say that your detector is on Y. Okay. What you would do? You You give a 90x pulse because you cannot detect your proton as a longitudinal axis. You need to bring it to the xy plane. So you give a 90x pulse or 180x pulse. 90x pulse, right? When you give a 90x pulse, your magnetization, all the spin would come as a coherent signal on Y, where your detector is. Now, as soon as the radio frequency is gone, it would start precessing on XY plane, right? So it would move in front of detector XY plane, full circle in front of a detector. And if I tell you that detector is now on and radio frequency is off, and that magnetic field is ever present, and that it is actually dancing on XY plane, moving on XY plane, and at the same time losing the angle to go back to the thermal equilibrium, you would understand what I mean. Your detector would start detecting it like this, then it is going into the other side of the circle, then it is coming back, and then it going other side, and then you would see that detector is detecting this magnetization vector which is moving on the XY plane with the precision frequency inherent to it and slowly moving out of XY plane towards the Z, and then there would be a time then you would have no signal on XY plane and your detector would not have any impedance or AC current on it. This particular type of decay is your NMR spectrum. Is primarily your NMR spectrum. And this is called free induction decay. And I want to finish at this point of time. Free because now at this stage, you don't have any other force. B naught is ever present. B naught is ever present because without B naught, you don't have NMR. But you don't have any other force. And it is freely decaying. Free induction decay. There is no induction of any other energy. The only thing which is actually happening that it is freely going away from the XY plane, dancing on XY plane, going out like an umbrella when you close the umbrella, and then umbrella is upside down, So when you close the umbrella, it goes up. But at the same time, remember, it is actually moving on the XY plane and then closing it. So, you see, this is a nice beat, a very nice beat. This actually represent the decay of a signal, and decay of the signal is representation of a relaxation of a signal. If I tell you that this is the T1 for metal, you should not really be worried about this. I can tell you, right? Although it is T half, T1 half, because T1 is when it goes to the highest energy state and then it relaxes back. But it is T half. Who cares? It is relaxation time, right? It is relaxation time. So this is the relaxation time, and if I give you a spectrum in which you have three different types of these beats. For instance, this is methyl, this is CH2, and this is phenyl. And if I give you this, without giving you the structure, you would not be very happy because these are just beating signals. These are resonance signals, free induction decay, right? And what it is? Number one, it is time, and it is called T2 time, small t2, small t2. And what I'm saying right now, I would come back to it. So please don't be worried about, don't worry about this because we will actually discuss this multiple times. I never understood that back in 100 years ago when I was trying to learn NMR spectroscopy from a very famous professor, Lloyd Jackman, who wrote the first book on NMR spectroscopy, a physicist. He was the first one who explained to me that this free induction decay is NMR signal. And he said that chemists should not really ask for anything else. And he said that if I give you 5 T1s, different 5 T1s, you should know that there are 5 different types of protons. And as you use frequency, you should be able to have correlation tables in which you compare that this T1 is because of a methyl, or this T1 is because of N-methyl, or this T1 is because of a phenyl, or this, and you should be able to interpret a data. And he was insisting on it, you know. If you go and find his book, Lloyd Jackman's book, NMR Spectroscopy, written in late 70s, is a fascinating book in which he insists that people should really use T1 rather than frequency. This was physicist's view. He said, you really save a lot of time if I just give you T1s, because these T1s are representing the energies, and energies are the precision frequencies, and precision frequencies are because of the electronic environment. So different T1 represent different types of proton. So you should be able to interpret the data of T1 into a structure also as you do the frequency domain. Okay, I was never convinced, because I didn't understood at that time. Simple reason. Now I understand that this is a free induction decay, and I would never be happy to find this, because imagine this is just a very simple case of 3 different types of proton. Assume there are 3 different types. You know that you would not really like my statement. There are so many different types of proton. Imagine if you have a protein, or even you have cholesterol, or you have penicillin, or you have a vinblastine, you would have 30, 40, 60 different types of beads like this. And they all are detected by the same detector. You can't have a different detector for different peaks. It's practically impossible. They all detected by the same detector. So what you would see is we need to make it work actually somehow. A nightmare spectrum. Where is nightmare spectrum? This one. This is your spectrum. Representing a lots of different types of beads coming out of different types of proton. You're not happy with it, right? You don't like it. Therefore, long time ago, somebody said, we need to do something. We need to convert this time signal into a frequency signal which is easy to interpret in a conventional way. हमारी problem ये है that NMR, we start benefiting from NMR when it was an absorption spectroscopy. If NMR has developed as it is today, we probably have been interpreting only the T1s, as we do in lots of other things too. But since we know only the frequencies, there must be a mathematical process to convert this into, okay. Now, this is called free induction decay, representing the relaxation. We do lots of things on this. We do a lot of things on this particular beat, a lot of mathematical process. For example, if I ask you a question, that if you see a beat like this, together, all 3 of them together, where is the more contribution of noise, in the tail or in the head? Where is the more contribution of noise? Because noise is random, always there in different forms and different. Where is the more contribution as compared to signal? Tail, right? You agree with me that the relative contribution of noise and signal is more favorable here. This noise has a less contribution in the head as compared to tail, because in the tail you have less of a signal. आप agree करते हैं इससे? Do you agree with this? Yes? कर लेना.
No, sir.
I really want people to provoke this question. Why?
No.
No, nobody wants. Okay. So the contribution of noise is more in the tail and the contribution of signal is more in the head, right?
Yes, sir.
So the tail is important, because without tail you can't have a cow, without tail you can't have a buffalo. Tail is extremely important, right? And some animals have only tails, nothing else. I've seen a spider monkey which has only tails. And the tail, there are small eyes and a small body attached to it. But the rest is just tail. Okay. Why we start discussing all animals and anyway? Okay, so this is the tail and this is the head. You see, if I were to tell you that tail is important, not because of the reason why I told you earlier, but because of the fact that most of the finer structure, so-called resolution of a signal, is also embedded in this part. If you lose them, you get a good signal, but you lose a finer structure, so-called splitting of the signal on the top of the signal. So if I tell you that I want to multiply this whole FID, can I do multiplication with this signal? Can I do that? This is the analog, lines. Can I do any calculation with the lines? So what I need to do? Okay, and for instance, if I want to record this whole signal, how many time I have to record. For instance, this is one peak from here to here. How many times I have to record number? At least how many sampling I need to do in terms of number? Nyquist frequency. Okay, just forget it. You need to have at least 3 numbers. One for this, one for this, one for this, and one for this, in order to have a full signal. At least 4 numbers. Right? Forget it. Forget the numbers. We just all convert it into a reasonable number sampling. It is a very important phenomena that how many times you sample this in terms of number. Remember, you cannot convert the whole analog into indefinite numbers. You need to sample them. If I give you a number in a graph, if I give you a number in a graph that plus Z10, 20Z plus 60 minus Y, you would be able to make a graph for me, right? So you would be able to convert a number into analog lines, right? But you need to have a sufficient number in order to make a correct line. If I just give you a few numbers, you would never be able to make a correct graph, right? So sufficient sampling, conversion the analogs into digital by a sufficient numbering is extremely important. Not so many, because then you overflow the memory of computer. That is a problem, because this is the reason why lots of people have actually gone into the dimension of Nyquist frequency and what I'm talking about. Forget it. This whole thing, if I want to multiply the whole thing with a factor which decrease the contribution of tail, what benefit I would have? I would have a time, I would have a benefit that I decrease the noise, right? On the expense of resolution. If, right? Forget everything what I said in last 10 minutes because this is just too much for me and too much for all of you. Kindly remember this FID is converted into numbers by a routine called ADC, analog to digital conversion. And these numbers are then transformed into frequency by a mathematical calculation developed by two very fine mathematicians of the world, Cooley and Tukey, two people. They have developed, and this is called Fourier transformation or Fourier synthesis. These time domain signal is converted into frequency domain signal by a process called Fourier transformation. Fourier transformation. This is the process 3 induction decay, which is the time is converted into frequency by a mathematical process called Fourier transformation. Fourier transformation is a mathematical black box through which you can convert one quantity into other quantity, and it is used in lots of spectrophotometric technique. It is used in X-ray, it is used in IR, FTIR, Fourier transformation, IR. All X-ray machines are Fourier transform now because you convert an electron scattering power into electron density by using the Fourier synthesis called Fourier transformation. So this process is called Fourier transformation, and it is critically important. Now, the last sentence. Why it's called pulse Fourier transformation? Because pulse is given, FIDs are converted into frequency by Fourier transformation. PFT NMR spectroscopy. Pulse Fourier NMR spectroscopy. Okay, I leave. I don't know. आज कितने बजे तक discuss करना था? 5 बजे तक? 4:30 तक. I want you to ask me question right now at this stage because I want to make sure that that we all are on the same wavelength in order to transfer the energy. We should be in resonance. All of us should be in resonance. Field strength is the system. Okay. At the end of this this discussion, I never call this teaching or course because I hate it. At the end of this discussion session of a month or so, you would be able to design your own NMR sequence. Absolutely, and I tell you, if I need to have a simple proton NMR spectrum, the question which I asked you earlier, what I need to do? 90 X pulse, turn on the detector, record the FID, do a Fourier transformation, I have an NMR spectrum. Any advantage of doing so? You see any advantage of doing this particular process in which I have a 90 X pulse, which eventually we would represent by a block diagram, so-called 90 X pulse, bring the magnetization from longitudinal to the transfer detector, record the FID, convert the FID into frequency. If I have ethanol, I have 3 signals. If I have ethanol, so many signals, right? Any advantage of this one with reference to the conventional absorption NMR spectroscopy? Any advantage नजर आता है इसमें? नहीं, chemical environment through absorption से पता चलता है. Frequency is absorption. You see, frequency either you can record it directly by sweeping the radio frequency, or by the relaxation. Right? Question is, any advantage of pulse FET, pulse Fourier transform NMR spectroscopy and a conventional NMR spectroscopy? How sensitivity increase? This is just one experiment, and you do the one experiment by continuous wave. Yes, please. You are not recording any interaction. You bring them on XY plane, let them relax, and you're recording the FID. And FID is then converted into frequency spectrum, and frequency spectrum is exactly the identical as you used to do by conventional absorption spectroscopy. No, one is, she said that you save a time, because you remember what you were doing was you were sweeping mostly the baseline. 0 to 12, ethanol, only 3 peak, 90%, 95%, you're just sweeping very carefully the baseline. So you waste lots of time. In this case, you excite them all together, you let them relax, and then you record FID quickly, and then any saving of time is visible in this whole concept. पहला मेरा क्वेश्चन. Absolutely. In the absorption spectroscopy, you were doing the whole process of absorbing it all the way to 180 very slowly. Here you just use 90x, and therefore absorption is instantaneous at the same time, and relaxation is half of what you used to have, right? So you save the time, right? Now, आप क्या कह रहे थे? अच्छा, आप क्या कह रहे थे? Yes. You see, this capacity of bringing magnetization to XY plane at a different position and then predicting it, that number one, where it would be when you give a specific predefined pulse. Number two, where it will move in a specific delay, came later. These all experiments of homonuclear, heteronuclear, scalar, dipolar came much later, when you got this capacity of understanding. The first thing was the sensitivity, and I want to explain why pulse Fourier transformation was a major departure for sensitivity. For example, if you want to do a so-called signal transposition by using continuous wave NMR spectroscopy, if you identify noise and you want to record noises, you record 10 different NMR spectra on a plastic, one over the other, spend lots of time and identify which peaks are random, because these peaks are noises, and which peaks overlap exactly on each other. That's how, say, noises become the part of the baseline and signal strength each other, and therefore signal to noise ratio increases. It takes lots of time. In pulse Fourier transformation in spectroscopy, you have this capacity of doing it so quickly. What you do, you bring magnetization vector here, record FID, give another signal. When you give another signal, it's the second experiment. Remember, it's different experiment because your magnetization vector has achieved a thermal equilibrium. It's already achieved a thermal equilibrium. So you wait for a while unless you record an FID. Then you do another 90x pulse, right? Then you record an FID, and you keep doing it 32, 64, 100 times very quickly. You don't do anything. Now at this stage, once your experiments finish, then you put all the FIDs together, convert them into numbers, do so-called Fourier transformation, record an excellent. Reason? Because in FID you also have a contribution of noises, as you had in continuous wave, right? And this contribution of noises are random in every FID. So at the end of the day, when you do a Fourier transformation, you would have a better signal to noise ratio. And remember, better signal to noise ratio is sensitivity. And that is the reason why Richard Ernst got Nobel Prize for it. He got a Nobel Prize because of a simple fact that he changed the whole paradigm of NMR spectroscopy. You see, people get Nobel Prizes for lots of things. But there are certain Nobel Prizes which are really Nobel Prizes, right? You get Nobel Prize of Peace by Nelson Mandela, and you get Nobel Prize of Peace by President of the Big Brother, right? There's a hell lot of a difference. Now, there is a difference in Nobel Prizes. This Nobel Prize is a seminal discovery because it's a major departure where the theory of the technique has been changed absolutely different. And you got this tendency of doing things so quickly and increasing the signal to noise ratio, because the biggest challenge in NMR spectroscopy is the sensitivity. So if in conventional wave spectroscopy you used to have 8 hours of 5 gram of samples, 5 milligram of a sample, now you can do in 8 minutes. 8 minutes. You do in 8 minutes the same signal to noise ratio, which basically means that you need to have 5 milligram of sample to get the same signal to noise ratio, and you have, for pulse Fourier transformation, you need to have 0.5 milligram of sample and or less of it. So you go in the domain of using less and less, needing less and less of quantity to get better and better spectrum, not by using hardware. You're not developing further hardware. You're not changing hardware at all. The only thing which you are now doing is a different thing. Changing hardware, developing large hardware was one way of developing technique, much simpler in approach. We was developing large magnets. But this is the technique in which, without improving the hardware, you improve the sensitivity by using a different approach altogether. Now, I want to tell you why you need to wait for so much time that it goes to the thermal equilibrium. If I am a thinking scientist, I would say as soon as it really moved 45 away from the X5 plane, I would give X5 45 pulse. I say further time. Because I understand that the contribution of noise is more in the tail. And tail is the component which is representing when it's going up. So I don't want to record the tail. because I can always add tell by using mathematical equation. Remember, if I truncate my FID here, if at this point I turn off the detector, I know that my magnetization vector is just somewhere in between xy plane and z plane. It's only 45 in between 90. And I want to give the second experiment I would do on a 45 pulse. And I'll bring it again to the xy plane. But then I don't record the tail. Tail is not recorded. Tail is only recorded when you have a complete recovery and the detector is on until the end, until it is recovered, go back to the original equilibrium position. I don't want to do it because I can add the tail by mathematical operation. See, I can just add numbers in terms of a mathematics. I have numbers for this. I just add 2, -2, -1, 0, finish. I can add tail by using an apodization process called apodization. I don't want to confuse you. I want to tell you that it has so much of liberty and power that you can do NMR in a much faster way. Instead of waiting so long that it goes back to the 90, you can stop it in between. What you need to have is an absolute calibrated equipment that you know precisely how much time it takes to go to the 45, and then you know precisely how much duration of a pulse is required to bring it to the 45. If the calibration of pulse is wrong, every time you take it to the wrong position. For instance, if your 90 pulse is not a 90 pulse, but it is a 100 pulse, where it will go? First 90 pulse was wrongly calculated. It is not a 90 pulse, but the duration is good enough to bring it to the 100. Where it will go? Below the plane, right? Yes? The second 90 pulse will bring it further down. And this cumulative error would make an experiment absolutely useless. Because every time you're giving a pulse, you're adding an error into the system. Right? So that's why calibration is done so promptly, very, very carefully. Calibrating pulse is the most important routine which an NMR spectroscopist does apart from shimming. Making sure that your magnetic field is homogeneous by using G, X, Y, whole range of different types of magnetic coiling. Question? Minimum? Minimum signal. Minimum signal means minimum signal. Why you want to have minimum signal? He is probably referring to some other technique in which we could probably go and see what it meant by this. But always remember, in order to have a maximum signal, you need to bring your magnetization vector exactly in front of your detector on XY plane. If it is up or down, you would have minimum signal. You see, T1 is mainly responsible of relaxation. T2 is mainly responsible of loss of coherence. T1 ही होता है, big T1. negative signal NMR is represent when you have a gyromagnetic ratio in negative. And number one, when you give an absorption signal, the phase changes also. Remember, negative signals primarily mean that you have in the different phase. You do in a polarization transfer and so-called APT, attached proton test, which when you distinguish between different types of carbons on the basis of their multiplicity. This is but negative NOE होता है, negative signals तो phases होते हैं. Phase, because you have a line, you have an up signal and you have a down signal, and these two signals represent different types of multiplicity. NOE can be negative. NOE can be negative. It depends on the size of the molecule. Anything else? Yeah, it is calibrated. It is calibrated. Actually, when an equipment is installed, they do it manually. It's very, very easy. It's trivially easy. Because remember, you would have a maximum signal when you would have exactly 90 signal. So you give different duration and you eventually find a duration when you have a maximum signal. That is your 90 pulse. Okay? ये समझ गए ना बात? Pulse किस तरह calibrate होता है? Because you start giving different duration of pulses and you turn on the detector. Eventually you would reach to a stage when even you pass that stage and you identify a time in which you have a maximum signal. That maximum signal is the signal where you have your magnetization exactly on the XY plane, which is called 90 pulse. Right? Huh? Gyromagnetic ratio can also be negative because this is a constant, and magnetic susceptibility can be negative also. Negative gyromagnetic ratio implicit eventually in a clockwise rotation of magnetization or an anti-clockwise, but the net result is same. You see, here we are dealing only the excess of population. The excess of the net absorption in the excess of population called M naught, which is represented by bulk magnetization vector. When you provide a 180 pulse, they go to the high energy state. What do you mean by all the nuclei? Excess की बात कर रहे हैं. This is because only the excess would absorb. Remember, the excess is a net absorption, is an excess of absorption. The difference is in the population difference of alpha state and a beta state is the species which absorb and go to the higher state. I want to tell you something very interesting. I forgot to tell you that this relaxation time, this FID is a small t2. Small t2, t is a small t, a small t2. You would be surprised to know that back in early 70s, even before that, people were using this T2, small T2, not big T2, because big T2 is a spin-spin relaxation, always remember. The small T2 for acquisition of signal or so-called FID. And I was always wondering why at that time people have used small T2. Even at that time, there was an understanding, which I would tell you later, that there can be another time before it. Almost, जिसे कहते हैं ना, prophecies जिसे कहते हैं, almost intuition of very bright mind that this acquisition is something which you are recording, but we should be able to do something in between, which can be T1. Long time ago. It was only Gina who explained it, but just forget this thing right now. It is this acquisition is called acquisition. Recording, FID, the detection. You can have different names. The scientific name of this process is called accusation. Accusation of data. Accusation. ये वो accuse वाला नहीं है, right? Is accusation, acquiring data. Yes, please. Thermodynamic. It goes back to the thermodynamic. This is a relaxation, this is a half relaxation time. Yeah, but always remember, you see, now you're not really scanning the baseline. Continuous wave mein, you were spending lots of time on baseline. Here, you are actually detecting the signals only. Therefore, the timing of recording acquisition time is much smaller as compared to sweeping the frequency for a long period of time. Always remember. Right? And now you have the capacity of doing this experiment multiple times. So many times, and when you do it so many times and you put them together, you improve the signal tonalization, and that is called sensitivity enhancement. Sensitivity. Okay, any question before I end here? It's a little premature. When we will talk about off resonance, then we will discuss about the off resonance. It's a little too early for discussing. Yes, please. Yes, radio frequency for different nuclear species is different, and it depends on the precision frequency. So you initially, when people have done it, अब तो हमें पता है, we know which length is which particular radio frequency is. But initially, people have been scanning the whole spectrum of radio frequency from 100 up. ये it's not even ये तो hertz में होती है ना. It's not even so it's not even in nm. So they were scanning the whole spectrum, and they were actually finding the window for proton and window for carbon, and that's how. Now we know that from this particular portion of radio frequency to this particular frequency is for proton, and this frequency is for carbon, this is for fluorine, and this is for all. They're also, it's called multi-nuclear probe. Even the probes were specially designed for proton only. They call proton probes, because they were very sensitive and they had a radio frequency oscillator absolutely tuned to the radio frequency of proton. Then they designed proton-carbon probes, which have two different types of coils, which were capable of exciting both proton and carbon two radio frequency oscillators. And there is a multi-nuclear probe in which you have so many of types of radio frequencies which you can give at the same time. T1 bada.
Hello, sir. I have a question, sir. Sir, if 360 pulse of RF is given to the sample, does this sample come back to the relaxed position or not, sir?
It is not in hertz. It's always in megahertz. Always, because magnetic power is very, very. The difference in relative precision frequencies of different nuclei is in hertz or kilohertz. Difference होता है ना? If different proton, they are in hertz or kilohertz. But the radio frequency pulse which you provide, it's actually in megahertz. So आपको question अब क्या है? दोबारा repeat कीजिए with the megahertz word. 360 megahertz.
No, 360 pulse of RS is given to the sample.
Yes.
360
Yes.
degree.
Yes.
360 typically would bring it back to the longitudinal magnetization vector with an increase in overall energy of the system, quantum mechanics. Duration you calculate. Always remember the most easy way of calculating the duration is to calculate the duration of 90. Because 90 is the pulse which gives you the maximum signal. And then you can say 3 microseconds requires to have exactly 90 pulse. So 6, 9, and 12. It is different in different nuclei and different in different instruments also. You calibrate pulse angles. You calibrate. This is and it's not one-time calibration. How long? कितने वक्त के बाद? Every month you calibrate. We have to calibrate pulse for every sample. Not the shimming. Shimming is altogether different. It's a deuterium log for chloroform. Because we've already set a deuterium log for chloroform. Therefore, you'd like to do all the CDCl3 sample at one after the other. Because if you change one after the other, every time you have to do. आप बोले पीछे. You have to do 90 experts. You see, always remember that your detector is placed on X5 plane. And your detector need to see the signal. And it can only see the signal when it is. Yes, I mean, क्या नहीं कर सकते दुनिया और कुछ. Mगर I think it's an important question. I want to deliberate upon it. ये जो when I say about magnetic, it is oversimplification of the fact that this magnetic power B naught is always on Z. There are always component on the transfer plane also. I mean, magnetism is never in a straight line, always remember. They have a direction. So therefore you like to keep it to the minimum position. जब आप magnet बनाते हैं सबसे narrow cone कहाँ पे होता है? बीच में होता है, right? Magnetic vectors का सबसे narrow cone कहाँ होता है जहाँ minimum dispersion होती है? It is in the center of the magnet. Therefore you always keep your detector. What do you want to do? You want to avoid the contribution of magnetic field, because if there is a contribution of a magnetic field which is constant, then it's overwhelmed the system and your tiny little differences. Always remember, when we would learn about rotating frame of reference, what you're recording is not in megahertz. You're recording the difference in one proton with reference to the other, which is always in hertz. अभी ethanol का जो signal है, the ethanol, the methyl, CH2 and OH do not have difference of megahertz between their chemical shift. It is only few hertz. So therefore, sensitivity of FID is of prime importance. And that's why you want to record it free of any influence. And that the optimum place for detector to be placed is on perfect transverse plane. Somebody wanted to ask questions from somewhere. Thank you. गाड़ियाँ चली गई होंगी क्या? God, नहीं, I think it should. Oh, I'm really sorry. मुझे अभी पता चला है, honestly. I'm really sorry. Somebody must really tell me. कोई जाके ना जल्दी से कहे रोकें, अगर नहीं तो वापस ले आएंगे. 5 बजे जाते हैं ना? Okay ji, Allah Hafiz. I'll see you inshallah 1:45 tomorrow. Allah Hafiz everywhere. Thank you.
Assalamualaikum. Assalamualaikum.